Good morning, my name is Porsche, and I'm pleased to introduce you to my talk on mapping overpressure distribution in the North Sea using deep learning techniques applied to fault interpretation. My supervisors for this project are Dr. Eric Larson from Earth Science Analytics and Dr. Gareth Roberts at Imperial College London. First, I will give a brief introduction and some background on pressure studies in the North Sea, followed by an overview of the project and the geologic setting. Then, I've divided this talk into 3 sections. I will begin with the deep learning fault extraction process and its results. Then I will explain the overpressure analysis. Finally, I will discuss the overpressure distribution as it relates to the deep learning extracted faults. But first, why should we be concerned with overpressure in the subsurface? Well, the identification of overpressure within the subsurface is critical to preventing catastrophic events such as blowouts in the field, as well as reducing costly incidences of caving, stuck pipe, and lost circulation. Reservoir compartmentalization, or the segregation of hydrocarbon accumulations into individual pressure compartments, is the result of bounding features in the field that prevent flow. These bounding features can also allow pressures to build up. Compartmentalizing features can be classified as tectonic, faults for example, or stratigraphic, caused by heterogeneities including erosion and pinch-out, or a combination of both. Previous studies applied fault transmissibility models onto manually interpreted fault maps and calculated low transmissibility between compartments with higher overpressure differences, identifying isolated pressure compartments bounded by faults within the basin. Here is a map to indicate the approximate location of our study area off the coast of Norway. The aim of this study is to identify individual pressure compartments within the Middle Jurassic sediments over a portion of the Viking Graben in the North Sea, and the role faults play in the distribution of these compartments in overpressure. This study utilized a 3D seismic survey covering an area over the Horta platform and into the Viking Graben, as well as repeat formation test measurements for 60 wells and available wireline logs for 109 wells. Deep learning fault extraction was used to map faults over 3 horizons: the base Cretaceous unconformity, the top Brent horizon, and the top Dunlin horizon. The base Cretaceous unconformity was used as the vertical seal in my pressure analysis. Pressure data from repeat formation tests and wireline log analysis was then used to identify the distribution of overpressure within the study area. Finally, the results were used to identify individual pressure compartments and create a map of overpressure. To introduce the geologic setting, here is a stratigraphic column over the Viking Graben in the Horta platform. The Middle Jurassic Brent group sediments, the focus of this study, are outlined here in red. The Brent group is made up of 5 formations, including the Broom, Rannoch, Edith, Ness, and Tarbert, and is a succession of deltaic, regressive, and transgressive sediments. For this study, the Osberg Formation is time equivalent to the Broom Formation in Norwegian waters. Here's an uninterpreted seismic line to give you an idea of the Graben structure and the transition to the Horta platform. The base Cretaceous is this bright reflector here. Adding some interpretation, you can see multiple normal faults and a steep drop-off as you move westward into the Graben. This is the result of multiple rifting episodes in the North Sea that ended in the early Cretaceous. Also, sections of the Jurassic are missing along the Graben flanks where the base Cretaceous unconformity has eroded the fault block crests. This is a simplified line drawing just to highlight some of the main structural features. Next, I will introduce the deep learning process and its results. Deep learning neural networks allow artificial intelligence to find patterns and features in data and use this information to make predictions. For this study, I used supervised learning, which uses labeled input and output pairs to train deep learning algorithms to make these predictions. Here is an example of an uninterpreted seismic line, and our process begins with fault interpretation. Faults on a selection of inlines and crosslines were manually labeled. An example is shown here with the blue lines representing the labels. Because my study focused on Jurassic age stratigraphy, my labels focused on faults below the base Cretaceous unconformity, although where faults crossed this horizon, the labels were continued. Models were then trained using these labels and selected hyperparameters to identify faults. After training, model predictions were reviewed for accuracy. Here, the yellow lines indicate the model's predictions. If they were accurate, the model was applied to the entire survey. If not, the labels were checked. If the labels were accurate, the hyperparameters, which control the training process, were adjusted and the model was retrained. If the labels were not accurate, the labels were adjusted and the model was retrained. This process was repeated until an accurate model was achieved. Then that model was applied to the entire survey and the fault volume was extracted. Deep learning models rely on precise labeling, and model reliability is directly related to the quality of the labels used in training. Reviewing my models during the training process showed that initial models struggled to make accurate predictions within the graben, sometimes not making any at all, where the discontinuities and seismic horizons were harder to follow. To overcome this, I adjusted the labels and added additional inlines and crosslines to the training set to give the model more examples in the graben. Here, the predictions from models 6, 17, and 30 show how the model improved over the training process, predicting more continuous faults over the platform as well as predicting faults within the graben. The location of this crossline is indicated here by the yellow line, and this surface is the result of the fault volume extracted from model 30 over the top Brent horizon. The red box indicates the area most models struggle to predict faults and also corresponds to the deepest section of the graben in the study area. The deep learning model was then applied to the entire survey, and the fault volume produced was sliced along the 3 horizons used in this study. This is the result of the deep learning fault extraction. Here, the deep learning extracted fault volume was sliced along the base Cretaceous unconformity, the top Brent horizon, and the top Dunlin horizon. These maps are colored by depth and two-way time, and note that these scales correspond to each map. Faults appear as black lines, and areas with no data correspond to areas where the horizon exceeded the depth of the seismic data used for this study. The graben appears as a smooth area over the base Cretaceous unconformity. This horizon is less faulted than the others, but some of the major north-south trending faults that bound the graben occasionally cross this horizon. The top Brent and top Dunlin show similar fault networks, although the top Brent has more continuous faults that link up more often. Deep learning fault extraction predicted the fault network in great detail over the top Brent horizon, capturing 2 dominant fault orientations, north-south and northeast-southwest, related to the multi-phase rifting that occurred during the formation of the graben. Next, I will introduce the pressure analysis. Repeat formation test measurements were available for 60 wells. This data was imported into a Jupyter notebook and quality checked to remove the duplicates and apply unit conversions. Then, overpressure values were calculated by subtracting hydrostatic pressure from formation pressure. Plotting the overpressure values on a map shows a general trend of increasing pressure towards the west, with the highest pressures occurring over the graben. The location of this map is outlined here in blue. Using the repeat formation test data, I looked at depth and lithology as factors in the distribution of overpressure. Box plots of the individual formations within the Brent group, shown here from shallow to deep, and used as a proxy for lithology, show a similar distribution of pressures with no obvious outliers. Plotting overpressure as a function of depth, with the hydrostatic pressure equal to 0, shown by the blue dotted line, shows a scattered non-zero distribution, with an overall trend of overpressure increasing with depth, although a linear regression gave an R-squared value of 0.53, indicating that there's not a strong linear correlation between these two variables, with the distribution appearing to have a more exponential relationship. In addition to repeat formation test measurements, wireline logs were available for 109 wells located within the study area. Using known velocity, porosity, and compaction relationships, normal compaction trend lines were calculated and applied to sonic logs to identify overpressured zones. Using an idealized response to overpressure due to disequilibrium compaction as a guide. Here, idealized responses for the resistivity, sonic, density, and neutron logs are shown. Reversals from the normal compaction trends were used to identify a transition into an overpressured zone. Results from the normal compaction trend line analysis for well 32-1 is shown here. Wireline logs include the caliper, gamma ray, sonic, resistivity, and density log. The sonic log is also shown here, with the normal compaction trend line plotted over it in red. These blue lines indicate the top Brent and top Dunlin horizons as they occur in this well. Normal compaction trend lines were parameterized using velocity relationships between initial porosity and compaction wavelength. Then the normal compaction trend line was fit using a qualitative approach to adjusting to get a good match to the overall structure. Here, a reversal from the compaction trend was interpreted as a transition zone into an area of overpressure. This well has direct overpressure measurements of 30 megapascals and was used to test this approach before applying it to wells without direct pressure measurements. Unfortunately, results for wells with suspected overpressures less than 25 megapascals were ambiguous. Clear reversals from the normal compaction trends could not be identified, and this approach was abandoned due to time constraints, although further work could refine the technique. Overpressure values for wells with direct pressure measurements were used in cross-section, shown here, to identify which faults, if any, acted as boundaries. The Brent group is outlined and colored by pressure value, with red indicating high overpressure, yellow moderate, and blue hydrostatic. Offsets that exceed the thickness of the Brent group appear to divide one pressure regime from another. Plotting well locations colored by overpressure value over the deep learning extractive fault map at the top Brent horizon shows pressures increasing towards the Graben, with major north-south trending faults separating pressure compartments. Using the top Brent horizon as the base, here's a map of the distribution of overpressure. For this map, overpressure was divided into 5 pressure groups, with red indicating very high overpressure exceeding 25 megapascals, orange high at 10 to 24, yellow moderate 9 to 5, blue low 1 to 4, and white hydrostatic pressure. Using the major faults identified in cross-section that offset the Brent group by significant distance, the fault network was used to bound individual pressure compartments, resulting in a map of overpressure that is segmented, with the highest values occurring over the Graben and a more subtle transition over the Horta platform. In subsections of the map, faults did not link up directly and were extended to complete compartment boundaries, given that offsets below seismic resolution would not be predicted by deep learning models. Overall, this distribution closely matches previously published maps, showing an increase towards the Graben center. Deep learning models did, however, allow for a more refined local map because of the detailed fault network it was able to predict. In summary, as deep learning models have increasingly become a part of the seismic interpretation workflow, my study highlights the importance of precise labeling to produce accurate predictions. Using deep learning models allowed me to map a significant area over the Viking Graben and Horta platform in a relatively short period of time. This study also demonstrates that overpressure in the Viking Graben increases towards the center, with major north-south trending faults playing a significant role in its distribution. A drawback to using deep learning to predict faults is the amount of training time. Creating quality labels in training models takes time. Additionally, models trained on one set of data will not give accurate predictions on another set and will require new labels and more training. To overcome this, future deep learning models that utilize active learning could reduce the number of new label sets needed. Active learning allows artificial intelligence to prioritize which data needs labels and actively queries users to provide these labels. The pressure study done for this project relied on pressure measurements from wells, giving limited data coverage. Future pressure analysis using velocity-based approaches could give a more detailed and complete map of overpressure and allow for a more uniform and detailed map of its distribution. This concludes my presentation, and I would like to open this up to any questions.